themselves, go for it. But if you've got a big presentation, I think jump into it because I think everybody's met each other on the phone already. So yeah, I'm really excited to see Jen's presentation here. This is exciting material, and the brief intro I'd give to it is that dealing with multi-criteria methodology and overlays is great in a lot of respects, but the Achilles heel, so to speak, is this idea of normalization and making it so you can compare different types of criteria with each other effectively. And I think Jen's got a really exciting progress on that front. So Jen, will you take it away?
I don't think everyone needs to introduce themselves, but I just want to sort of welcome people to chime in at any point. I already foresee a couple points where I'm worried people will chime in a little too early, but we'll tackle that as it comes. So I also need to apologize that I seem to be having a problem connecting to ArcGIS products this morning. There's a disconnect between me and the license file that's located on our server. So I'm going to be doing all of this on PowerPoint, which I wasn't planning on doing, but luckily yesterday afternoon I took quite a few screen caps of some of the most pertinent windows, so we should be able to work now. So to get into our problem, to what we're working on very briefly. So John and I, with a couple other people with the Wilderness Society, are trying to create some type of approach to prioritize roads for closure, to recommend roads for potential decommissioning on the forest. So it really involves quite a bit of raster analysis, so this cell-gridded analysis that we're then summarizing to line files. And in this case, we're going to be talking about two files in particular. So I'm trying to skip over the intro work that goes into this summary. So I'm just sort of jumping in now, accepting that the ecological work behind what we've done, just please take that as like beautiful, perfect work. We could discuss that at a later date when I present this work overall, but I really just want to talk about how these results are summarized to the line and then how we work with these values. Are we all clear? Okay. So in this case, I'm going to use two different data sets as our examples through this discussion. So soil erosion and stream crossing. And you can see here, this is when I simply take the raster environment data and summarize by the line segment of these roads on the landscape. So just have a look. I guess everyone can see my mouse, correct? Okay.
Yep.
The big problem that we've been worried about all along was really the stream crossing data set. It is incredibly skewed and scared us, but soil erosion, to be honest, isn't that much better. But if you look at a histogram, it at least looks a little better in its distribution. So this is just some statistics of where we are starting at. Okay. So moving on, after looking at these values, we decided that we need to do something with them. We weren't exactly sure, but actually based on Randall's presentation a couple weeks ago, we saw all these three options from the MalGC model as an option. So maximum score range, and mid-value mean are three approaches that Randall's gone over. He outlines them on the website. And I think there's some webinars about them, although I haven't had the opportunity to watch those. So maximum score is one of the really common ones, and it's incredibly easy to do. It's a value over the maximum. And score range, the positive to a maximum score is really that it keeps your outputs in a proportional relationship. A potential downfall to that is that there are not necessarily a zero value. And score range, the positive to it is that you're guaranteed a 0 to 1 range. And this mid-value mean, we'll get into that later because that's really what we're applying here. So given our situation, though, with soil erosion, especially being the 0 to 3 with a maximum of 0.362, we elected to do an intermediary normalization, which I think I've already thought of a workaround to do. But so because we have a 0 value anyway as our minimum, we applied a maximum score to both of these data sets. So I guess before we apply the maximum score, here's the histogram. Sorry, my slides are out of order. This is a histogram of what these files look like to begin with. So This up here is soil erosion. This right here is a little stack of 0 values. But overall, it has a pretty decent curve. It does only extend out to this 0.362. Stream crossings is a much more worrisome data set, as I've already stated. There's an overwhelming number of zeros, which isn't necessarily a problem. I think that makes sense. There aren't going to be streams crossing every road, luckily. But there are some values. They're too small in this scale of histogram, and I'll be taking the scale in later images to see. But there are enough values distributed across the bottom. There aren't very many, but they are distributed. So it was with this data set that we elected, these two data sets that we elected to apply a maximum score normalization method. So that is the value over max, and this is actually what happens to the mean. So now our min and max is for both data sets 0 to 1. Stream crossing doesn't change at all because it was 0 to 1 to begin with. And soil erosion changes significantly. So our mean jumps up to 0.45, and the mean without zeros, which will become more relevant in a couple of slides, you'll understand why I'm adding this in, is slightly higher at 0.464. In stream crossings, it's a huge difference because of that overwhelming number of zeros. So this is what the histograms look like for given this maximum score normalization. So just to be clear, I've removed the zeros so we could really see the distribution. I've removed the zeros in both. So up here on stream crossings, if we had every line segment represented, there would be about 100 zeros over here.
I think that
but and in the case of stream crossings, there'd actually be about 2,100. So again, it would flatten out and we wouldn't be able to see anything. So this is what the distribution looks like without those zeros. So there's the one.
We're not looking at distribution. Should we be seeing a graph?
Oh, can you not?
Oh, it just changed.
Shots?
Okay, right now we're seeing the histogram.
Yes.
That's right, I think. Yeah.
Janice, can you see a histogram right now?
Yeah, there was just a long delay.
Okay. Okay.
Looks
well,
good
then
now.
I'm sorry. I'll go back. So come back here now. So this up here, in each case, is going to be our soil erosion data set. So I have removed the zero value so we could see the histogram of stream crossings a little bit better. But in the case, just be aware that there would be about 100 zero values right here. But that distribution still wouldn't change. And for stream crossing, there would be about 2,100 zero values. But you can see that the distribution is all the way. There is some distribution across. So we have some around here at 0.5. I think there's even some at 0.74. They're just very few values. So, okay, so this is our result of the maximum score. And with this, we elected that this wasn't sufficient. So we've decided to move on and apply what we're calling a mid-value mean. It's similar to the mid-value method that is described in Maldusi's book. But, and in this case, we're just going to do it simply where we, instead of just using the simple midpoint or having someone define a midpoint, we're using the mean as our midpoint. So we're setting the mean equal to 0.5, and 0 is our min, so 0 is 0, and 1, 1 being our max. So you can see the huge difference between both of these lines. And instead of trying to find an equation that can fit the lines, find a type of equation that can fit these points, we decided to just do straight lines between each segment. We only decided that after some guessing and checking and looking at different lines. And the real problem was this soil erosion was not difficult to fit. We could find a line that could work with it, but stream crossings was there aren't any options that we found viable. So, but we actually are okay with this approach so far. And for this point, we have only used one midpoint. There is also the option that we to continue adding midpoints, having 0.25, 0.75, 0.875. So for now, this data just includes these two lines, linear equations per data set. So after applying that mid-value mean, things changed significantly, especially for stream crossing. The soil erosion didn't look too bad to begin with, but it has gotten better. So our overall mean jumped to 0.487. It was at 0.45 before. And the mean without zeros is 0.502. So I think that shows how well our equations worked at balancing. And the same goes for stream crossing. So our mean going in after the maximum score was a 0.08. But after the mid-value mean is a 0.082, which jumped up from a 0.07. Not a significant change. But when we eliminate those 2,100 zeros and look at those 400 values that do intersect the stream, we find ourselves with a 0.516 mean, which made us pretty happy. So this is what the distribution looks like now. And again, I've removed the zeros. Otherwise, with the stream crossing, you wouldn't be able to see anything. But for soil erosion, we have a decent-looking histogram. We're pretty happy with it. It centers around 5. There's a little bit over here, but it's pretty good. And as far as stream crossing, it's a significant difference. It's huge. So we're really pleased and think it's working in the right direction for what we're doing. And I guess, again, I'm leaving out 2,100 zeros over here. I don't want to be deceiving, but we're happy with the distribution. So given using those distributions, this is the scenario of an equally weighted sum. So up here is a situation of no normalization. So when we use that initial summary by line, this is what our result looks like. It has a decent shape, but our maximum is 0.6, and our mean is down at 0.24. So, and things change just a little bit, but everything goes up a little bit in the after the mid-value mean, after both of these normalizations. And we appreciate the distribution.